Hey, welcome back to your favorite calculus class. We're going to look at applied optimizations problems. So this is where we're asked to maximize or minimize something. Um, and so we're going to be taking the derivative and set it equals 0, right? Because we want to find out where we have a relative max or a relative min, right, for the function. So let's look at this first one. You know, you may have seen this in pre-calc. Let's look at this. Suppose the height of an object straight up is given by h of t is 512t minus 16t squared. H is measured in feet, and t is in seconds. You may have seen this in pre-calc, and since it's a quadratic, you know, this is a flipped over quadratic, so something like that, right? You could find this vertex, which is on the axis of symmetry, right? X equals negative b over 2a, and find where that max is, right? That was pre-calc. Well, the problem is we don't always have a quadratic to do this with. And so we're going to practice doing it with calculus now. So where would the maximum height be? We want to find the max. Well, if we want to find the max of a function, we could go ahead and run the first derivative test. So there's our function. Let's take the derivative. We got 512 minus 32t. Let's set that equals 0. So it's 16 seconds. So here's our h prime. 16 seconds, our critical point. We could throw in h prime of, let's say, 15. And you're going to see it's positive, so the original function increases, right? That quadratic increases till 16. I could throw in like 17. You can see that's negative, and then it decreases, right? So we have a maximum right there. A max, max, not a mat. Max t equals 16. So we've got h of t, because we're looking for the max height, right? So at 16 seconds, we have a max. So what's our max height? Well, let's plug it into the height function here. H of 16, 512 times 16 minus 16 times 16 squared. This will end up being, let's see, 4,096 feet. So we have a max of 4,096 feet when we're at 16 seconds. All right, let's do another one here. Find two positive numbers whose sum is 15. Two positive numbers whose sum is 15, so that the product of the cube of one and the 12th power of the other is a max. So let's write that first statement. Number one, two positive numbers whose sum is 15. Let's call them x and y. So their sum is 15. Secondly, it says their product, let's just call P, their product, the product of the cube of 1, so the cube of the first number, and the 12th power of the second number. So their product is a maximum. So we're trying to maximize that function right there in red. I'm trying to find the maximum for that. Well, notice that from number 1, since x plus y equals 15, then if I solve for y equals 15 minus x. So let's go ahead and throw that in here so we can take the derivative with only respect to x here. And so we've got p equals x cubed times 15 minus x goes in for y to the 12th. And remember, we're trying to maximize this function. So let's take its derivative. Derivative of the first times the second plus the first derivative of the second. And derivative of that 15 minus x is just a negative 1. And so we've got the first derivative, we've got 3x squared times 15 minus x to the 12th minus 12x cubed times 15 minus x to the 11th. Let's go ahead and take out a 3 plus 3x squared and a 15 minus x to the 11th. And so we'd be left with a 15 minus x in that first term. We'd be left with a minus of 4x on that second term. And so we've got 3x squared, 15 minus x to the 11th, and then 15 minus 5x. Set that equals 0. So we get x equals 0 from that one. We get x equals 15 from that one. We get x equaling 3 from that one. So step 3. Now if we let x be 0, then our product is x cubed y to the 12th, right? We're trying to maximize this. Well, if x is 0, or actually let me write it this way, right? Then this would be 0, so I don't want to use that one. And notice for the 15, that's the same problem. If I plug a 15 in for x, that's going to make this part 0. And so the product would be 0. I'm trying to maximize the product, right? Therefore, the only one left, right, those are out. It would be the 3. The 3 would be the best one. If I let x be 3, remember x plus y equals 15. So 3 plus y equals 15. So y would be 12. X equals 3, y equals 12. Therefore, x equals 3 and y equals 12 will give you a maximum product. Give max product where, in other words, 3 to the 3rd and 12 to the 12th. We're maximizing that, right? Now this one we're trying to smallest perimeter. We're trying to minimize this, right? Smallest perimeter possible for a rectangle. Let's draw this rectangle whose area is 36 square inches. So what are its dimensions? What are its length and width? So number one, we're given that this area is 36 square inches. Well, we know area is length times width. So the area is 36. Now we're trying to minimize perimeter, right? So our perimeter is 2L plus 2W. So this is what I want to minimize. I want to make it though, I'm going to be taking the derivative of this, but I would like it all in terms of one variable. So I'm going to use the fact that since 36 equals L over W, W equals 36 over L. So let's throw that in right there. So our perimeter is 2L plus 2 times 36 over L. So P equals 2L plus 72 L to the negative 1. Now, we want to minimize this. So let's go step 3. Let's take this derivative with respect to L. And so we got dP dL equals 2 minus 72 L to the negative 2. We're going to set that equals 0. Multiply both sides by L squared. Divide both sides by 2. Square root, square root. I can't have a negative 6 length, so it's just a 6 here on that. And let's go over here to step 4. I have, if L is 6, W equals 36 over L. And we know L's got to be 6 to minimize this. So we got 36 over 6, or W is also 6. So our perimeter, 2L plus 2W, right? If I add up L plus W plus W for our perimeter, 2L plus 2W here, oops. Yeah. So yeah, 24. So this actually ends up being a square. Is a rectangle? Is a square a rectangle? Technically, yes. Yeah. So what's our dimensions? Length times width. 6 inches by 6 inches. That'll minimize, in this case, our perimeter. That'll minimize, like if you were trying to fence in that amount of square inches, right? All right, we've got an open box of maximum volumes made from a square piece of material, 24 inches on a side. Cut equal squares in the corner, turn up the side as it's shown on the right hand side there. First write an equation for the volume of the box. So our volume would be length times width times height, right? So we got length times width, and then our height there is at x right there. So our volume is 24 minus 2x times another 24 minus 2x, that's our width, and then our height is x. So there's the volume, and we're trying to maximize this volume. Right? So step 2, if we're trying to maximize that, let's go ahead and take its derivative. Derivative first times the second plus the first derivative second. 24 minus 2x. Now it's to the 1 power times derivative of the inside, which is 0 minus 2's. 2 there, chain rule on that. And so v prime of x equals 24 minus 2x. I can take a 24 minus 2x out. Factor that out, and I'll have 1 minus... No, I'm sorry, I'll have a 24 minus, there's 2 of those in that first one, sorry. So I'll have a 24 minus 2x, and then minus, it looks over here, I've got a minus 4x there from that term. And so we got 24 minus 2x, and I've got 24 minus 6x. So 24 minus 2x, that gives us x being 12, so that equals 0. 24 minus 6x, that gives us x equaling 4. Now we don't want x being 12 as the volume would be 0, right? If I threw 12 into the original function, that would make this right there 0, right? So that's not going to maximize our volume. So it's going to have to be the 4. You know, and if you weren't sure, of course, you could throw it in on both sides. And you can't have more than 12 either, because it would obviously mess things up there. So throw in like v prime of 3. You see that's positive, so we increase up to 4, and then we'll plug in v prime of like 5. That'll be a negative on that, so it'll maximize it at 4. All right, we'll have a max there. So x equal 4 will maximize volume. So here's our volume formula. Oops. We have x times 24 minus 2x squared. Throw 4. Let's find the maximum volume by throwing the 4 in. (24 minus 8), I guess 16 squared. 16 squared, 256 times 4, get 1,024. And this will be cubic inches on this. That's our max volume here. All right, here we've got a rectangle bounded inside this semicircle, right? Given by this function y equals the square root of 9 minus x squared. There you see that semicircle there. What length and width should the rectangle have so that its area is a maximum? Let's go ahead and write the area of this. You see how we have x plus x there? Maybe I want to do it in x plus x is that length there. And then its width is that height y. So this area is 2x times y on this. And remember, what's our y value? Well, that's the square root of 9 minus x squared, right? It goes up as high as that. That's the functional height. So our area here is 2x times the square root of 9 minus x squared once we replace the y with substitution. So that's what we're trying to maximize. Here's our area function, 2x times 9 minus x squared to the 1/2. So let's go ahead and take its derivative using the product rule. Derivative first times the second plus the first, derivative of the second. So I get a 1/2, 9 minus x squared to the negative 1/2. Derivative of the inside is 0 minus 2x. And so we've got 2 square root of 9 minus x squared minus, let's see, one of these 2's is gone right there. So minus 2x squared over the square root of 9 minus x squared. Let's get a common denominator. So give this a square root of 9 minus x squared. Square root of 9 minus x squared, which will undo the radical there. So the derivative is 9. Where'd that 9 come from? Sorry, that's a 2 right there. So 2 square root of 9 minus x squared times square root of 9 minus x squared is just a 9 minus x squared. That's 2x squared. This is all over that square root of 9 minus x squared. So a prime of x equals 18 minus 2x squared minus 2x squared. So negative 4x squared plus 18 all over the square root of 9 minus x squared. Let me write that a different way by taking a negative 2 out. Whereas a prime equals 0, where that 2x squared minus 9 equals 0, so x squared equals 9/2 square root, plus or minus 3 over root 2, multiply top and bottom by root 2, and this is a length. We'll take that positive 1, whereas a prime undefined, wherever that square root of 9 minus x squared equals 0, square both sides. So I have 9 so x squared equals 9 plus or minus 3. But if you notice, if I was to let x be 3, it would cause my area, if I throw it in right here, see how that'll be 0? 9 minus 3 squared to 0, 0. That'll cause my area to be 0. So cause area. Remember, we're trying to maximize the area, so I don't want to use that. So therefore, I'm left with that 3 root 2 over 2. Therefore, 3 root 2 over 2 will maximize area. So we've got this area function. I got 2x times the square root of 9 minus x squared. Let's throw in 3 root 2 over 2. And we've got 3 root 2 square root of 9. That'll be minus 9 halves. 3 root 2, and I've got 18 over 2. So that'll be 9 halves. 3 root 2 square root of 9 is 3. Square root of 2 square root of 2. Those will cancel. Looks like I've got 9. That's our max. Area is 9. And the dimensions, the length was 2x by the height of y, right? So the dimensions would be 2 times that, 3 root 2 over 2. The height is y. So if you throw in, the y was square root of 9 minus x squared, right? So if you throw in 3 root 2 over 2 squared, you get the square root of 9 halves, which is 3 over root 2. So our dimensions here end up being 3 root 2 by, rationalize that, 3 root 2 over 2. That's our length and width of that. I'm going to cut the video off right here and do a second part next time. Thanks for watching. Now let's take a look at this example here. We've got a rancher has 200 feet of fencing. That's like to enclose these adjacent corrals that are shown below. What dimension should be used so that the enclosed area will be in max? We're trying to maximize area. Well, number one, we're given that we have 200 feet of fencing. All right, let's go ahead and write that down. We're given 200 feet of fencing. Let's see how much fencing we're going to use. Let's call this whole top part from there to there y. So that'd be the bottom as well, y. Let's call these lengths of the fencing x. So all that fencing, let's call it the perimeter here, is x plus x plus x, so 3x plus 2y, and we have 200 feet for this fencing. 200 feet, 3x plus 2y. Now, what we want to do is we want to maximize this area, right? So area would be length times width. That would be how much area we have. Area is x times y there. That's what we're trying to maximize. And so what we'll do is let's go ahead and take this perimeter and let's solve for y on this. So let's subtract 3x from both sides so we can get this down to one variable. So we have 200 minus 3x equals 2y. So let's go ahead and divide both sides by 2 and we'll have solved for y there. And now let's go ahead and throw that in for y right there. So we have this area. So step 2 is to solve for a variable, and we're going to throw it in here and substitute. So area equals x times this y, which is 200 minus 3x all over 2. And so we've got, let me come over here. I'll continue with this here. Area equals, let me distribute this through and put them all over the 2. And let me come over here. So here's our area formula. Area equals, in terms of x, 100x minus 3 halves x squared. And we're trying to maximize that. So we're going to go ahead and let's take the derivative on our critical points. Most our 2's cancel here. So let's find our critical points. Add 3x to both sides. So we got 100 thirds. So 100 thirds will maximize the area. So in other words, if you went first derivative test, you would see that it increases and then it decreases. So we're going to have a maximum there at 100 thirds. So we know x has got to be 100/3. So what would our y be? Well, our y was 200/2 minus 3x/2. So our y is 100 minus 3/2 x. And we know our x is 100/3. So we have 100/250. 100 minus 50 ends up being 50. So finally, what's our dimensions? X by y, our height by the length there. It'll be 100/3 feet, our x, by our y, which is 50 feet. So that would be our dimensions that would maximize the area of the enclosure for the two adjacent corrals. This one looks like we got a poster. It's got 50 square inches of printing. That's that inside part with a 4-inch margin at the top and bottom, 2-inch margin at each side. Now we're trying to minimize the amount of paper used. Let's call this length right here, let's call that y. So on the top I have 2 inches and then y and then 2 more inches, right? So that top would be y plus 4. And then down here I'd have 4 from there to there, and then I have x, and then I got 4 more inches right there. So that whole side length would be x plus 8. There. And we're trying to minimize the amount of paper used. So we're trying to minimize that whole area, right? Well, what are we given initially? Well, we're given x times y is the 50 square inches, that inside area, right? The inside area is given. That's x times y, which is 50 square inches. So we're going to go ahead and solve for y, solve for one of the variables again, so 50 over x. Now we're trying to minimize the whole area, right? How much paper we're using. We're trying to minimize the whole area. Well, the whole area would be x plus 8 times y plus 4. But again, I'm going to go ahead and substitute. Y is 50 plus x. I got to put that in right there. So I'm just left with one variable on this. And then when I go ahead and multiply this through, I'll have 50x over x, so that's just 50. Outside x times 4, I got 4x. That would give 50 times 8 is 400 all over x, and then plus 32. So it looks like I've got 50 plus 32, I've got 82 plus 4x plus 400 x to the negative 1. So I can go ahead and take this derivative so we can minimize this. Derivative 82, of course, is a constant. Derivative 4x, derivative constant is 0. Derivative 4x is 4. And then I've got negative 400 x to the negative 2 when I take that derivative. And so I'm going to go ahead and set that equals 0. I got 4 minus 400 over x squared. Let me add 400 over x squared to both sides. Oops. Let me come over here. So I've got, let me multiply both sides by x squared. Divide both sides by 100. So I get x squared, or divide by 4, so it gives me 100. And square root both sides. So I got plus or minus 10. Well, this is a length, so we're just going to take that positive 10 there. That will minimize the amount of paper used. All right. So step 3, now we know we want to have x being 10. And we also know that x times y was 50. So 50 equals 10 times y. Divide both sides by 10, so our y ends up being 5. So finally, step 4, our dimensions that we're going to use for this entire poster would be x plus 8 by y plus 4. Well, x is 10, y is 5, so we got an 18 by 9 inch what is this, poster or whatever, to minimize the amount of paper being used here. Looks like we've got a 108 cubic foot box here, so they're giving us a volume, right, with a square base and an open top. Square base, open top. So let me call this like x and x, and this height y here. It's going to be constructed from sheet metal. Find the dimensions of the tank with minimum weight. So we're trying to minimize like our surface area. Minimize the weight. You know, the amount of sheet metal that you're using. You know, surface area is kind of like if you painted it, right? So our surface area would be, if I was drawing this, you have a bottom, you know, that would be the x times x, right? That would be the bottom. That would be the x squared, okay? Plus, how much more if you were painting this? But of course, we're not painting it, plus we're using sheet metal here. But each panel, let's do this front panel. We have x times y, right? That's a panel right there. And we've got how many of those? Well, we've got those two, and then the back one, and then that other back one. It looks like we've got, oh shoot. One more. Oh, I kind of made a mess of this. But we've got 4 of those XYs. And that's our surface area, right? Now, we're given, and that's what we're trying to minimize. We're given this volume. You see the 108 cubic feet box? So our volume here is x squared times that height y. That's our volume. It's given as 108 cubic feet. And so the easiest variable to solve for, since the degree of y is just a y to the 1, is I'm going to solve for y. So I'm going to divide both sides by x squared here. So I have y equals 108 over x squared. And I'm going to go ahead and throw that in right there. So let's see, step 3, we're trying to minimize this surface area. I got x squared plus 4xy. So our surface area is x squared plus 4x times our y, which is 108 over x squared. Let's see, that's 432 all over x. So I'm going to write that as x to the negative 1, so I'm going to take the derivative here. So the derivative, this is all in terms of x, is 2x, and then 432 times negative 1 minus 432, and then x to the negative 1 minus 1 to the negative 2. I'm trying to find our critical point here that will minimize this. I'm going to add 432 over x. Actually, you know what? I'm going to get a common denominator here. This is over 1, so let's give this x squared. And so we've got 2x to the third minus 432 all over x squared. Now, if x was 0, it would make this derivative 0, but we don't want to. That's not an option, right? We have to have a length there on the bottom. So x being 0 is not an option to minimize this. So we're just left with that numerator. If that numerator is 0, then let me add 432. 2x cubed equals 432. divide by 2, I got 216. Let me take a third root, in other words, to the 1/3 power, and we get 6. So we know we want that x value to be 6. You know, the square box bottom is a 6-foot length. And then we also have y equals 108 over x squared. Let's throw in the x. So we got 108 over 36. So we get y is 3. So our dimensions of this, you know, we got length times, so that's x times y, x, another x. That's the square base bottom, right? We have x times y dimensions by y. So we are 6 feet by 6 feet by a height of only 3 feet. And that will minimize the amount of sheet metal that we use to build this. Of course, we have an open top on this, right? But, thanks for watching. See you next. And taking notes. See you next time.